Welcome to Brain Vision.
Problem 7.77. We're designing a pendulum exhibit for a museum. Such things actually do exist. The pendulum is relatively realistic. It has a mass m and a length L. M doesn't matter. L we're finding in part A. And so what we've been up to so far is plotting the tension in the pendulum string for different starting heights of the pendulum bob. And point 8 here is when the pendulum is stationary, it's 0.8 meters above the ground. And so this is just the tension due to the weight of the pendulum. So we have this table. The first thing we want to do is plot this tension versus the initial height and figure out the length of the string. And then we're told that if the breaking strength of this wire is 822 newtons, what's the maximum height you can release it from if you're not going to exceed half the breaking strength? And then C, we're given a scenario where we leave the pendulum swinging at the end of the day. We leave the museum, nobody gets in overnight. We get back the next day and pendulum is just standing still, hanging there. And using some energy considerations, we want to explain how it is that this happened. So for part A, here's a plot of the a plot that's been derived from the table we're given. And here's a best fit line that's shown. You can any sort of thing that you like plotting with, you can have it produce a best fit line. So here we know that the conservation of the mechanical energy is going to give us the initial potential energy is equal to 1/2 mv squared plus mg h naught. So this is at the bottom of this swing. This is our 0.8 meter minimum height of the bob above the floor when it's standing still. And then applying Newton's second law using the centripetal force at the bottom of the swing tells us that the tension in this swing, then the tension in the string or the wire is equal to the centripetal force plus the weight of the bob. So now if we combine these and set up t as a function of h, we get t equals 2 mg over L times h plus a constant mg 1 minus 2h naught over L. So the slope of this is going to be 2 mg over L. And so the best fit equation for this gives us 9.2 293 newtons per meter for this, and then for this, not for h because that's a variable, and this is a constant 257.3 newtons. And so 2 mg over L is 9.293 newtons per meter. We know that mg is our 265 newtons per meter. We know 2 mg over L. We can just solve this for L. And this ends up being 57 meters. Which sounds like it might be extremely long, but if you ever actually go to a museum that has any sort of pendulum setup, like with a Foucault pendulum that displays the rotation of the Earth under it, they end up taking up, you know, several stories of a museum out in like sort of a lobby area, vertical space all the way to the roof of the museum, and so they end up being quite long, and so this is not actually unreasonable. Now, for part B, we want T equals 411 newtons. So using the equation we just had in part A, we have T equals, let's call it this alpha H plus T naught. Alpha is our 2 mg over L. T naught is this. It's not really not in the sense, I mean, it's, well, no, it is, yeah. It would be at zero height of the tension would be. Or it's what the, yeah, when height goes to zero, this is the tension, but height never goes to zero. But anyway, let's not worry too much about it. Just need some symbols to not end up with a bunch of confusing numbers before we actually have the expression we want. So this is T minus T naught over alpha. So this is 411 newtons minus 257 newtons divided by 9.293. Sorry, 9.293 newtons per meter. This will be H. And this gives us 16.5 meters. Which, if you recall, the length of the wire is 57 meters. So this is actually quite possible. You're not like lifting it up above the pivoting point of the pendulum or something. And now for part C, this is pretty quick. Basically, the pendulum starts off with some kinetic and potential energy, with some total mechanical energy, let's say. But as it swings, air resistance and friction with whatever is the pendulum wire is being mounted from are going to do negative work on it and cause it to come to a stop. Friction from air and contact point, let's call it, where it pivots to negative work.